Good morning. I'm here from Intel. For many of my friends here in the audience, I used to be not long ago at HRL Labs. The big exciting thing about this whole field for Intel is that it seems to be coming to a point where there is potential value proposition options that are emerging over maybe the next few years. And so what I'm going to talk about, I'm just new to Intel. I joined in January of this year. So my talk is going to be more about a landscape talk in terms of what machine learning was, what is it today, and what we think it could be in the future, and how Intel may play a role in some of these technologies going forward. So with that introduction, so please bear with me in terms of some of the things I'm going to say. You must have heard of it and maybe even sick of it by now. But the first generation machine learning, that is the past, was what we call shallow supervised learning algorithms. And so notwithstanding Hopfield and other ideas, like we saw this cartoon so many times over in this conference, you have this feed-forward model. There is sort of biological analogs for various elements of the network. For example, synapses would be those weights. Dendrites would be those arrows getting into those transfer function blocks. Then there's a dendritic trunk, which then sort of feeds that information to a cell, and which then processes that and sends out some information out. And you put together networks of these neurons to represent a so-called an artificial neural network. And conventional machine learning was developed based on this layered architecture, where the goal was to abstract away as much detail as possible, keep it as simple as possible, and then see what we can do with this. And functionally, what they wanted, for example, Rumelhart and others who talked about this way back, the idea being is to learn an input to output transform or a mapping, and you would do that in the context of where you have a supervisor that provides some sort of ground truth, and you use the so-called feed-forward fully connected architecture where information flows from the input units to the output units as shown in this cartoon. And the learning algorithm essentially was based on this idea of gradient descent, where you would use the error between the desired output and the actual output. And based on differentiable functions such as sigmoidal neurons, you would sort of figure out a way to assign credit and blame for the various weights in the network. Early models, the reason why it didn't really get beyond it, so basically was shallow, was because of this local minima problem that gets worse with the depth of the network. And so shallow learners, as we like to call them, that required handcrafted feature data in order to sort of minimize the number of layers that you want to use in the network. So we're talking about thousands of parameters, but also these systems were so susceptible to, if you think of things like irrelevant features in the data. So that's just 2 slides for the past. Now, the present. So we're talking deep supervised learning ideas. So the idea being that you have multiple modules with a feed-forward network to compute a nonlinear input-output mapping. And the idea here is that if you can allow many layers, many number of neurons to process information, and it's still a feed-forward manner, but then if you can do that, then the hope is that you would get increased selectivity and invariance to representation. So it still abstracts details away. I mean, we heard Christoph's talk yesterday as to the level of complexity in the neural system. Assuming it can abstract away all those details, then there were 2 major approaches that actually drove this field forward from the shallow learners to deep learners. One of these ideas was this idea of contrastive divergence for feature detection from unlabeled data. So the cartoon on the top right there shows this idea is that you have some data that comes in through some neurons called visible inputs, and that gets sort of, let's say, projected onto a hidden layer. And then there is this process of back and forth between these two to sort of set up a system where the inputs can be predicted by the hidden layer units reliably. And then you do this over and over again through many such pairs of modules to sort of set up the system where it's a good auto encoder. So it would sort of, each layer would be able to encode its features in the layer below it. And so if you put this stack together and then you do backpropagation on this pre-trained network, so to speak, you would overcome the local minima problems that were a big issue with the shallow learners. So that enabled deep learners, and this is the restricted Boltzmann machine idea. And then there's also, in parallel, there's another idea which is people talked about it yesterday, this idea of pooling of semantically similar units after doing some convolutional filtering. Originally inspired by Fukushima, the HMAX algorithms, and then Jan LeCun as well, who applied backpropagation to this idea of layers of convolution and pooling called convolutional nets that allowed us to sort of get over this so-called local minima problem, if you will, in the shallow learners. So the deep learners, they're trainable with large depths, millions of parameters, using raw data. So that is a huge deal, and that allowed systems that could be automated, sort of fed with real-world data from video streams or from audio streams and so on. And the good thing about this was because it has all this, the depth in it, the information, like I said earlier, was able to show increased selectivity to the object details, but not the background. So, and the big reason for why deep learning is everywhere today are three factors. One of them is obviously you have fast enough computers enabled by Intel chips, for example, with affordable large memory, availability of large data sets for training and benchmarking, obviously. And then, of course, this whole bottleneck, overcoming this bottleneck using deep learning technologies such as restricted Boltzmann machine and convolutional nets. So, if you go to any of these conferences, in fact, computer vision conferences are dominated by deep learning methodologies that extract information from videos, does all kinds of stuff pretty reliably and very impressively. And so that's all good, and so that's where we are today. Deep learning has been explored both from the software and hardware perspective for tackling real-world problems. And in the companies, as you all know, including Intel, by the way, is looking into this. Okay, now let's look at what I call as third generation. And this whole term coined neuromorphic computing was originally by Carver Mead at Caltech in the late 80s to sort of describe analog circuits that mimic neurobiological architectures in the nervous system. So that was basically a coin that was originally developed by Carver, which lately, what got morphed into this idea called neuromorphic engineering/computing, which was introduced to expand the scope from just not analog circuits, but also include digital mixed mode, analog digital VLSI, and also software systems. And so neuromorphic computing today would encompass all these different ideas. And so revisiting this ANNs from what we saw before, this cartoon that we showed earlier. So look at the object. The output function is basically some nonlinear function of the inputs. And that's where we were. But the reality of it, even if you look at some phenomenological models from neuroscience, time is very implicit in the neuronal dynamics. I mean, you cannot ignore the fact that all these various entities in the equations that are modeling, like Hodgkin-Huxley and every other equation that you model, including leak, integrate, and fire, the conductances are functions of time and voltages. And these are implicit in the dynamics. While you can wash away those details which led to astounding success, it's there in the making, and so the question is, what does that add to the value here? Of course, we heard from Christoph and others about a whole bunch of features that are prevalent, morphological features, large connectivity, we're talking 1:10,000, laminar structures, layered architectures that seem to repeat itself, with recurrent networks where networks of excitatory and inhibitory neurons put together in arbitrary configurations to realize very complex dynamics. Some of the features that seems to be interesting, at least to Intel to look at, is some of these ideas. So the idea of asynchronous processing with spikes that is both efficient and scaling. So there's lots of evidence for brain being asynchronous. There's lots of rhythms in the brain, but there's no particular global clock. So there's evidence for it at all levels, retina through V5, parietal, prefrontal, and other cortices. And some of the more compelling ones for Intel as in terms of hardware is the idea that you can encode analog information using a single wire. So the so-called action potentials or spike signals, Aurel Lazar, who's probably here in this audience somewhere, is one of the people who showed that you can actually encode reliably in the interspike intervals useful information from an analog signal. So what this means is it's going to offer you area efficiency and scalability. That's the first point. And the second point being that these events, so-called address events or events that sort of mimic some sort of a salient activity at a neuronal level, dissipates power only during the spike events. So there's energy efficiency, so to speak, from that. And then there's also the challenges in transmitting analog information long channels, where you have to transmit both the amplitude and the timing information, can be overcome if you have some assuming signal regeneration. You can get reliable transmission of spike signals to long distances, thereby ensuring reliability when you actually try to put millions of these guys together. So these are some of the interesting things. But then starts the complexity as slowly starts to build up. If you sort of look at it as factual evidence as we know today, there's a variety of plasticity rules, which is probably key to learning. One of which is reweighting, which we've all done in the ANNs and the deep learning frameworks, which is mostly synaptic in nature. But then there's all these other things, the rewiring, where it refers to the processes that create or prune axonal arbors, which are more structural in nature. There's reconnection that refers to processes that form or prune new synapses, which are both structural and synaptic in nature. There's regeneration that refers to the processes that create or remove neurons, which is structural in nature as well. And last but not the least, seems like there's new discoveries that are talking about reparameterization, which basically refers to changes in the physical parameters. For example, conduction delays. There's a beautiful paper by Douglas Fields talking about how the myelination in the axonal arbors can change, causing changes in the conduction delays, adaptation of the delays itself, which is another interesting variation to the whole story we know about. The other important point is that memory and processing, as we know it from our Intel architectures and what we are dealing with here, are very different. So we call it, the Intel, the von Neumann machines are weakly co-located, meaning they're physically and functionally separated. Memory and computing are physically and functionally separated. And in terms of biology, they seem to be strongly co-located, meaning that they're physically and functionally very tightly coupled. And in particular, neuronal activity seems to enable changes in synaptic efficacy and structure, while synaptic changes in turn also affects the neuronal transmission and interaction. So that's a huge, big difference, first of all. And then synapses seem to multiplex to be part of multiple memories. They're distributed in nature. And the memory is accessed by indices that, typically that are not related to memory content in traditional architectures, but in biology, they seem to be able to recall complete memories from partial cues. The notional idea of content addressable memories, one of the pioneers being in this audience here, doing that kind of stuff. The other thing to notice is that this variability and multi-scale interactions is the norm. It's not something you try to shy away from. These are things that exist, and our factual evidence is for that. For example, Christoph talked about a numerous number of cells, cell types, genetic expressions for these cell types, and so on, is the norm. There's a whole bunch of, we just talked about axo-dendritic synaptic interaction. There's a whole bunch of other, synaptic means by which communication happens. Axo-secretory, axo-axonic, axo-dendritic, extracellular, and some of which are dendro-dendritic, and a whole bunch of others. And so this seems to be a norm as well. There's a whole bunch of this. And it seems like plasticity itself, there is a state dependence as well as time scales for these plasticity mechanisms. So what I mean by state dependence is that it depends on some cases on the pre and the postsynaptic state of the neuron, of the spikes that get through the neuron, or maybe just the postsynaptic neuronal states, or just the presynaptic inputs such as transmitter-induced, as well as time scales. There's a whole span of different time scales. We heard about synaptic facilitation, depression, and so on, fast compensatory kind of plasticity, all the way to spike timing, and then homeostatic, which are in the orders of minutes to maybe even days. So, and many of this, sort of you can further classify them as Hebbian or non-Hebbian, depending on the causality and how that was established. And last but not the least, it seems like the structure, even if you knew the structure, the structural network, the dynamics seems to dictate the functional connectivity. So even though two neurons may be sort of physically not connected, when it actually comes to executing a particular behavior, it seems to be functionally linked together through this dense network of connectivity, which is sort of very intriguing from the point of view of how this computing really happens. So if I put all this together, one conclusion we can draw is that nervous system is a complex system. I don't think there'll be much debate about that. It's a collection of many, why? Because it's a collection of many interacting units, billions of them. The collective behavior is affected by both memory and feedback that can change with time. And the collective behavior can also adapt their history to improve performance. And they are open thermodynamic systems, meaning they're influenced by the environment constantly. Now, in terms of the traits of them, so the system is spontaneously active. There is no switch off mode or power off mode where nothing happens. It's a system that is far from equilibrium. It's spontaneously active. It exhibits emergent phenomena that can be surprising sometimes, not programmed in, so to speak, as to everything is sort of predictable and programmed in, which is good and bad. These phenomena can emerge without any invisible hand or a central controller, which is also very interesting. And it seems to seamlessly move between order and disorder, which is sort of extremely interesting. And the big takeaway here is one of the things is that it exhibits consistently a rich set of macro states, behaviors, but with very little dependence on its microstates or billions of parameters. Specifically, if we were to actually sit and tune our neuronal parameters to actually behave in a reliable way, we would be out of luck. We would sort of not survive at all. So the question is, how does this self-organization, so to speak, happen in order to realize consistently a rich set of macro states or behaviors from a bewilderingly complex space of microstates? So I have 3 slides. So at this point, this is where Intel is scratching its head about really what is its role here and what we want to do in this space. And so there are 3 slides I have here that talk about some of the ideas and some of the thought process at Intel. It's very new. The whole thing is, I just joined in January, like I said. My colleague, Mike Davis, is in the audience, who's been at Intel for a little longer than me, but both of us are sort of scoping it out at this point. So one of the success would demand understanding the essential elements or principles of neuroscience. So I talked about some of the things that exist, but the question in particular would be how to build self-organizing dynamical systems that is scalable, meaning that you could put, if you sort of want to add more neurons and synapses or whatever you want to do with it in terms of size, that it naturally scale, while exhibiting the capacity to learn from its interactions with its environment in a stable and robust fashion, something where you can sort of it's a reliable system that can be provably robust. Is obviously a tall order, but it seems like there's something that's of great interest to Intel. Now, as you know, we have innovated over the years in terms of a process innovation. There's a whole bunch of technologies out there today that could be brought into sort of become part of this whole exercise here. Some of it, for example, X-point memory. It's a transistor-less system that is somewhere between DRAMs and flash. Gives you much more dense memories and non-volatility, but which is sort of new, and so products are expected to come out very soon on that. A whole slew of technologies, 3D integration side. I can't say too much about it, but there are some ideas there that are very, very interesting and relevant, maybe. This idea of optical interconnects, where you have 1.6 terabits per second interconnect speeds that are possible today with real technology that exists. It's not some of this pie-in-the-sky thing. It actually exists. There's a whole bunch of others from the device technology side as well that Intel has put its focus into, not really for neuromorphic in particular, but it seems like it could be relevant going forward for what we want to do in this space. Now, the question to ask is how to leverage our state-of-the-art process technologies and other core technical competencies to build such a self-organizing system. What is the what is the core set of ideas or things that would make sense from a neuromorphic perspective. And then last but not the least, this idea demands searching a solution space. It's all about making money in the end for Intel. And it has to be a value proposition that makes sense. When I say value proposition in terms of scale, performance, power, cost, just a notional sense from going from processes and devices all the way to applications with the range of programmability and all the way back to benchmarking and refinement of these various elements in the vertical stack to make sure that we have to answer this question, which is what is the ecosystem, hardware and software resources that is necessary to create a strong value proposition from such a system. So this is where we are today, very early days for Intel in this space, but very excited to be here and looking forward to maybe potential collaborations with some of you to see where we can take this. With that, I'll stop and take some questions.
I'll start with one. So you mentioned a number of forms of plasticity, and of course, neurogenesis is something I like, and other, Paul's talked about the dendritic growth and so forth. From a hardware perspective, have you had any thoughts about how these sort of structural plasticity implementations could emerge at a more chip level?
Right. There's for now, I don't see in the foreseeable future anything that things like wires growing out of these chips. No chance. But having said that, some of the obvious ones would be if you had density, then you would have redundant resources on the chip to sort of use it that way, if possible, to program it or connect it up together or wire it up together to do some things that are interesting. Neurogenesis, for example, or sources like that. But certainly, early days for us, we're not really, we are sort of scoping the landscape of what we need to do here. Some of these things are obvious, seems from all the talks and from the neuroscientist perspective. Seems like we don't want to sweep these under the rug because they seem to be there, and it's always the question as to what is it doing, and the same old things come up over and over again. So the question is, are we there yet to sort of start thinking about pushing the envelope to do something that is revolutionary and not evolutionary? And so Intel wants to put money into such a technology if it means it's going to be a revolutionary value proposition. So, yeah.
I'd like you to talk a little bit more about one of the statements you made, that the brain exhibits a wide variety of macro states without much sensitivity to micro states.
Yeah.
Now, I could take issue with you there, because if you've ever had a toothache, that little nerve can occupy your whole life and control how your thought process is unfolded.
So what I mean by that is, if you just take a neuron, right, and you take, it has dendrites, it has all these, phenomenologically at least, there's all this range of parameters, time constants, a whole plethora of constants and thresholds and so on. And if you may have billions of those, you're talking of a huge number of variables that we have to potentially figure out how to, sort of set up in order to have a hardware that works reasonably. If that is what we have to do, then it's really not, Intel is not interested clearly, because that's something that's going to be ridiculous in terms of complexity. So that's what I meant by saying microstates, in the sense that all the state variables that are dependent on time and voltage and that change and that have all these constants that you have to deal with and set in order to make the system behave in a certain way at the global scale is what I'm talking about.
Okay. I think, though, such a system has to accommodate the fact that a very small perturbation can actually influence the whole system. In fact, that might be the way nature set it up.
Right. So the sensitivity, it depends on the modes in which it operates. I mean, if it's at the edge of chaos, as Wolfgang would call it from before, that is more sensitive to smallest to small perturbations. Whereas if it's subcritical or modes where it's very stable, maybe it may not be, it may be able to tolerate it. So it has all these modes. It's not necessarily one or the other. And so the question is, how does it even, do that? I mean, so that's our question. I mean, yeah, automatically, self-organized.
Thank you again.
Thanks a lot.